Okay, perfect. So again, welcome from my side. Um, I'm not sure what you've heard so far, so I would just begin from the very beginning and make sure that we have the same standing here. I'm working at the ISIS, the Leibniz Institute for Analytical Sciences in Dortmund. I'm working as a PhD here, so I'm maybe not an expert as the previous speakers, but I will nevertheless try to give my best in this field, because what I'm going to talk about is basically on the content of my PhD thesis so far. The presentation will be about facets of ambient air diode laser desorption, plasma ionization mass spectrometry. The three key elements here are diode laser desorption, plasma ionization, and mass spectrometry. And I want to highlight some characteristics of that. First of all, let's talk a bit about plasmas. The bottom message of this slide is basically that we're not using blood plasma from the centrifugation of blood, but rather a low temperature plasma, which you have seen in the previous presentation from time to time as simply low temperature plasmas, LTPs, or DBDIs, dielectric barrier discharges. There are, of course, other plasmas, very thermal plasmas, or even lightning, which is more or less a plasma, but in a very strict technical sense, there are even some differences and deviations in that, but I don't want to bother you with the details. Here is just to take home that we are using non-thermal plasma, which you can also apply to your skin, for instance, because the gas temperature is low. That's the key element. So we're talking about ionized gas in the end. And the starting point or motivation for my thesis was basically a publication from a colleague of yours, which was working with me for quite a time here at ISIS, Bienvenida. She was working on pesticides and pharmaceuticals and all the stuff, that pretty fancy analytes you have in HN. We are more interested in the methodology of ionization mechanisms and all the stuff. So she used a diode laser and shot it. It was an infrared laser, by the way, and shot it on a microscopic slide on glass surface. That glass surface was doped with black ink dots. So she used a pen and dotted the glass surface. It was already almost 10 years ago, so it's been quite a while since then. And there were some issues with that technique, because the ink dot depends on the manufacturer and the solvents you're using, as well as the droplet that can spread all over the glass surface. So you're not able to confine it. So that was really the starting point where I thought, okay, maybe we can have some improvements in here to make it a little more reproducible. And yeah, this is basically the first setup that I got. It's still a microscopic glass slides, the ones you can buy from Thermo Fisher and similar manufacturers, but it's buttered with copper, so it's like a sandwich structure. You have a thin copper layer and a thicker glass layer below, and this was really the key element in the desorption, as you will see in a few minutes. Also, another point which is highlighted here is the flexible microtube plasma. You have seen this plasma in some previous presentations. The very cool thing about it is it's from the geometry. It can be compared to inverse low temperature plasmas, but without a grounded electrode. So you have this pin electrode inside a glass capillary. This is put on high voltage, but without any grounded electrode, which is quite cool, because it has some benefits in ion guidance, because it creates an electric field to the MS inlet. Nevertheless, in comparison to the DBDI, which was a glass capillary, just to give it a recall real quick, with two electrodes around this glass capillary, and the dimensions were about 1 millimeter, whereas the flexible tube has only an inner diameter of 250 micrometers. So we're getting really, really small with these plasmas, and we can get really close to the inlet, which is a quite cool thing, because you do not need any transportation line or any heated capillary to get the ions or the neutrals to the MS inlet somehow. Yeah, back to the surface again. I just shown you that we're using a copper glass surface, but there was something that I didn't told you yet. which is a little coating on top of the copper surface, because as I motivated or said, the droplet can spread on the whole surface. So one method or one option to solve this issue was that we just created small cavities. So you can see the picture of the copper here with 7 times 7 cavities, and each cavity has a diameter of roughly 1 millimeter. So this allows you to put your components, your standard analytes, whatever it is, inside this cavity, and then shoot directly with a laser from the top of from the top side to the surface. Again, the generation or the recipe for this substrate is a little more difficult, but in the end, our goal was to achieve a higher reproducibility with these desorption substrate. Yeah, and the cool thing about this sandwich structure was that we even had, so we used a very, very high concentration. We shot on the copper surface, and we were able to receive an ion response even after the 10th shot, which is kind of, so it has two sides. On the one hand, you would say, okay, well, you're not absorbing anything. Okay, we have a high concentration. That's the one side. The other side is, why we still have a signal. That must mean that there must be still some copper which heats the surface and then desorbs the analyte, because without heat you cannot desorb something. The desorption process is completely based on heat. It's just a matter of how fast you get the heat into the surface and yeah, how hot the surface is, basically, so the surface temperature. And then we realized that the copper is not ablated, so this is not laser ablation, but it's laser desorption. Although the copper is not fully in its in the first place, but it's rather trapped inside the glass. So it's very weird, because if you apply acids on this copper surface, you can get rid of all of the copper, but not this tiny dot inside the glass, which is basically the melted copper. And then we were in a little shock, because we realized, okay, if we melt copper, the surface temperature must be very high. And I promised you that I was working with Bien in the lab, and we realized, okay, if the surface temperature is, let's say the melting point of copper is 1,000 degrees, that surface temperature is maybe too hot to just get soft ionization. Oh, let's use it this way then. Here we go. So yeah, as I said, there's probably no chance for analytics, we thought in the first place. And these are some microscopic images of the results that we have. On the top side, there's just this plain cavity. And on the bottom side, if you go to increased laser intensities, you will see that something happens on the surface. You have, this is marked with the blue and red arrows. You can see that something really happens with the copper on the glass, and you can achieve in the end something that looks more or less like a black hole. And we realized that, okay, let's see what the mass spectrometer says. And in fact, the ion response or the ion signal increased with a higher surface temperature. So there was a quite interesting fact, because it's not only a question of laser intensity, but as you can see, we also decreased the application time from about 30 seconds to even 4 seconds. And I got one experiment with which I can't show you here, but I used the lower laser intensity and applied this laser for, let's say, 1 hour to the surface. And then I just increased the laser intensity a little bit for like 2 seconds, and I got a really high ion signal. So that was the moment we realized that, okay, maybe this isn't a question of how long you apply laser to the surface, but at what speed in terms of laser stability, and how high your laser intensity is. So there are two factors in the end: surface temperature and the gradient, how fast the laser is coupled to the surface. We even tried out other structures, so pure block metals, semiconductors, but the key element is that we need a sandwich structure, because we need to keep the temperature on the surface. It's not that efficient to have heat transfer all over the surface, so we need to keep it at a very, very thin layer to make sure that we can get the analyte desorbed. We also tried out like many analytes. So now we get a little more to the chemistry part here. You may know this solution already. It's quite a popular one. It's a calibration solution. You have some caffeine at roughly 200 masses. We have the ultramark peaks below 1,000 masses, and which cannot be seen here, the MFR peak, because it's not well ionized by plasma. But in the end, this plot shows that we can use laser desorption for quite a range, for quite a mass range. And I even tried out mass ranges up to 4,000, which is a little more complex, and I have the feeling that the efficiency decreases, but still there are some possibilities to this. So the first design I've shown you was that we had the laser applied from the top side. One drawback of this setup was that we were not able to fully screen the substrate, so we had to slice it each row, which is of course not really nice if you want to screen like several analytes, right? Because you have to use a wafer saw at a time. So we rotated the setup and now apply the laser from the back side, from the glass side of the substrate. Therefore, we were able to, on the one hand, decrease the distance to the MS inlet, and on the other hand, fully screen the substrate. Even the cavities could be seen from the backside. So that was really the next step. Although with a little drawback, because we have to apply the laser from the glass slide, so it has to go through the glass, and then it just is absorbed and reflected by the copper. And we compared it for cholesterol, and saw, okay, there are some differences in the ion current, but they are not really that bold. It's probably about 10%. It's not really a big deal here. So now we finally get to our more interesting analytes, except from mass calibration solution. I also tested, besides cholesterol, I tested cholesterol esters, which seem to show some fragmentation tendencies. I mean, cholesterol is still detected as a fragment, as a dehydrated cholesterol, but the ester also generates a fragment, which is also on the same mass. So you can see that there might be some issues with identification in more complex compounds. One of these complex compounds was a liver extract, a bovine liver extract. And you can see here that the dehydrated cholesterol at roughly 370 masses is the highest peak. Just to make that clear, we are using a very, very old ion trap here. So don't worry about the mass accuracy here. It's an LCQ ion trap. It's not a Q exactus or something. So the mass accuracy is not as far as high as with the modern mass spectrometers. But you can also see some lipids at 600 masses or 800 masses, which is quite cool, because this may allow to detect different compounds in a complex sample. Another interesting point in this manner was that cholesterol is desorbed at a quite low laser intensity, so we use it as kind of gold standard for our measurements. However, with other lipids at higher masses, the threshold was higher. But again, this is not a mass-dependent effect, but it must be related to the topological area or other factors of the compound. In that sense, there's even a publication, I think it's from one of your colleagues, I'm not quite sure about that. They used a heated substrate for desorption, and they stated in their publication that lipids are less efficiently desorbed. So this might add to the idea that each compound might have a certain intensity threshold for desorption, which you may know from gases. And this method is called temperature programmed desorption. This is usually taken, as I said, with gases such as nitric oxide or something, but it might also apply to even more complex substances. So this might be an interesting field to test in a controlled atmosphere like David presented, but with very lower partial pressure to control the rate of desorption. Yeah, so that would be a cool application from this side. Some other compounds that I tested are also come with a different intensity threshold. So this might be an interesting topic, although the arbitrary ion current is hard to link yet without without known pressure. Some topic I've been now working on is imaging. So I used liver tissue from mice and shot the laser on the tissue directly. We had a little different substrate design to get this working. As this presentation is recorded, I'm not really allowed to dive deep into that because it's a paper in submission, but that would be another application and perspective. So as a summary, so far I've found out that the sandwich structure is really a key element in terms of desorption, and the desorption is controlled not only by surface temperature but also by the gradient. This allows us to detect different standards, some without internal standards, and even perform calibration, for instance, on cholesterol. However, some of the lipids I've shown you, or the cholesterol ester, come with some fragments, such as the loss of the phosphocholine head group or the cleavage of the C chains. Nevertheless, these methods allows application in many directions, such as the controlled atmosphere or the imaging I've just spoke about. So in the end, I'm open to question, and thank you very much for your attention.
Thank you very much, Alex. Any questions? Although I really don't know now who is following you, but anyone having a question, go ahead and take it.
So, hi, Alex. This is Marcos. I just have a quick question. Did you see any ion when you used just the laser without the flexible tube?
Good question. No, we tried that out, just applying the laser to the surface without plasma post-ionization, and there were no ions detected by the LCQ ion trap.
Okay, thank you. And sorry, I didn't mention, but it's a really cool work. I told you about it, and I really like the presentation. Thanks.
Thank you very much.
More questions?
Can I make the question?
Sure.
Sure, yeah.
Alex, I'm sorry, I missed the first 5 slides. Can you repeat the characteristics of the laser?
Oh, yeah. Sorry. I think I didn't go that deep into the laser characteristics here, so I just pointed out real quick. We were using a diode laser in the UV vis, so at 450 nanometers, and at continuous wave operation mode.
Okay, thank you.
With intensities of roughly 10 watts per square millimeter.
Another question, you use a lens to focus the beam or no?
We're using objective, so you can see it in the picture. Actually, it's from a microscope. It's put in a microscope revolver, and this focused the laser on the substrate.
Okay.
So it's a lens system.
Mm-hmm. And another one, have you ever tried to align the beam waist of the focus point?
What do you mean align to the surface?
To align the beam waist of the characteristic length that the lens focus the light.
Yeah.
Have you ever tried to change the distance between the sample and the lens?
Yeah, that's something you regularly do when aligning the substrate. So you get into the center of a cavity, you align the depth or the length of focus to the surface, and yeah, you use basically the focus. I mean, it's not as good as with ND-YAG lasers, for instance, but because it's a laser diode and has high divergence, but it's definitely possible to some extent to focus it using anaphomatic prisms and this objective.
Okay, thank you.
I have a question. Alex, what is the total size of the diode laser and how much does it cost? I mean, it is something that it could be produced easily and not very expensive?
Yeah, I think the laser diode costs about, sorry if I'm mistaken, but I think it's like 100 euros or something. It's not that expensive for a laser, and the size is basically a box. So you can, I mean, it's like this surface. It's very, very small, or the surface of this glass. So you can basically put it anywhere, I think. So the laser diode is actually very small. The housing is basically the biggest part of the laser. The housing is just to keep the light of the laser away from the user. But the laser diode itself, it's like very small. It's like this big.
And the power, the continuous wave power is how much is?
So usually you use a laser diode controller for this purpose. I'm not quite sure what power the laser diode controller really needs. I just measured the power of the outcoming laser output, and then fixed it. There would be in the range of, let's say, 500 milliwatts, and compared to the surface, which is usually given by the laser intensity, it's about 10 watts per square millimeter. Although I'm not very sure how the costs are for the laser diode controller and how much you have to pay for laser operation. I'm not quite sure about that, but I think it's not that really much because you do not read high voltage. You just need, like, I think it's not entirely sure, but I think it's like 5 volts for operation of the Peltier element, and I think it's just if you up to 1 ampere for the laser diode, so it shouldn't be that much, of course.
Thank you very much for the information. Pambos, do you have any question, or you want to say something? Pambos is okay. So if there is no more questions, I think now we are at the end of the webinar. Thank you very much, Alex, for giving the opportunity to finish the seminar, and for being persistent and trying to fix the technical problems. Thank you very much. I really appreciate it. It is really good work. I'm looking forward to seeing your future progress on this thesis. And if I don't know if anyone has anything to say. Anyone wants to share their feelings?
Yeah, thank you very much
we are supposed to
keeping up and following the seminar.
Do you have any questions from, not only from Alex, but from any other speakers that you haven't done so far? Well, in that case, I would like to thank you all of the speakers and all of the attendees. I hope that we will save the presentation, and we will make it available at the TImPANI webpage for a few time. I hope we can do another webinar soon, probably in a few months, with new results and new data. And I hope you find it interesting, and please send any feedback of what you have thought about the webinar to either to me directly or to Pambos, and we will consider it for the following webinar. So if there is nothing left to say, I just say thank you very much, and see you soon. I hope you have a great day. Bye bye.
Thank you.
Thanks a lot. Bye.
Bye.
Thank you. Bye.
Thank you. Bye.